at a mountain so high that its base covers an area the size of an entire country. A mountain so vast that if you were standing at its summit, you wouldn't be able to see the edges of it, because the horizon of Mars would curve before your eyes reached the edges of this structure. A mountain so absurdly large that your planet's atmosphere can barely cover it. You wouldn't be seeing a mountain. You would be seeing something that should not exist. Something that defies everything that planetary geology has taught us about the limits of volcanic growth. You would be looking at Olympus Mons, and the moment you understand what it really is, the way you think about volcanoes, about planets, and about the raw power of cosmic geology will never be the same. Let's start with the numbers, because the numbers, here, are the first sign that something is profoundly out of the ordinary. Olympus Mons is 21.9 kilometers high, measured from its base. To give you a concrete human reference, Mount Everest, the highest point on Earth, is 8.8 kilometers above sea level. This means that Olympus Mons is almost 2.5 times taller than Everest. More precisely, you could stack 2 Everests on top of each other and still not reach the summit of the Martian volcano. You'd need 2 full Everests and a third of a third to finally touch the top of that structure. And that's not all. The base of Olympus Mons extends approximately 600 kilometers in diameter. 600 kilometers, for context, this is roughly the distance from São Paulo to Rio de Janeiro and then back halfway between the two cities. If Mons Olympus existed in Brazil, its base would cover almost the entire state of São Paulo. A single mountain, a single continuous geological structure. But what truly separates Olympus Mons from anything you've ever seen or imagined isn't just its height or its width in isolation. It's the combination of the two with something even more disturbing. The edges of Olympus Mons form an escarpment, a kind of vertical wall, which at some points reaches 8 to 10 kilometers in height. 8 to 10 kilometers. This means that the edges of the volcano are themselves almost as high as Everest. If you were to arrive by walking across the Martian plain towards Olympus Mons, you would not see a mountain gradually rising on the horizon. You would come across an almost vertical wall of rock with a height equivalent to the tallest mountain on Earth. And that wall would not be the summit, it would just be the edge. The true summit would still be more than 10 kilometers above you. Now think about that for a moment. Let this image fully install itself before we continue. Olympus Mons is officially classified as a shield volcano, the same type of structure that forms the islands of Hawaii here on Earth. Shield volcanoes are characterized by low-viscosity lava that flows over long distances before solidifying, building wide and relatively flat structures compared to explosive stratovolcanoes-type volcanoes on Earth. The largest shield volcano is Mauna Loa in Hawaii, measured from its base on the ocean floor. Mauna Loa is about 9 kilometers in total height, which would make it technically comparable to Everest in absolute height. But Mauna Loa has a base approximately 120 kilometers in diameter. Olympus Mons is 5 times that diameter, and almost triple the height. There is nothing on Earth, nor has there ever been on Earth, that remotely approaches this scale. And why? Why did Mars produce such a monster? The answer lies in 2 factors that combine in a way that Earth's geology simply does not allow. The first factor is severity. Gravity on Mars is only 38% of Earth's gravity. This seems like a technicality. It is not. When lava rises from a hotspot in the mantle and begins to accumulate on the surface, gravity is the main mechanism that resists the vertical growth of the volcanic structure. The lower the gravity, the lower the resistance to material buildup. On Mars, with less than 2/5 of Earth's gravitational pull, lava can stack vertically much more easily. The mountain can grow taller before the structure's own mass begins to collapse in on itself. The second factor is even more fundamental, and this is where the comparative geology between Mars and Earth reveals something extraordinary about how planets work from the inside. Earth is a planet with active tectonic crust. This means that the surface of our planet is divided into giant plates that move, collide, subduct, and move away from each other continuously. When there is a hot spot in the Earth's mantle, a place where magma rises persistently from great depth, that hotspot creates a chain of volcanoes over time. That's because the tectonic plate over the hotspot is always moving. Hawaii is the best known example. There is a fixed hotspot under the Pacific plate, and this plate moves continuously over it. The result is a chain of volcanic islands, where each island represents a different moment in geological history, with the oldest being the farthest from the current heat source. The hotspot remains active, but the crust has moved away, so the energy was distributed along the entire chain. Mars has no plate tectonics. The Martian crust is a single, rigid, immobile piece. When a hotspot appears beneath the surface of Mars, the crust does not move. The magma continues to rise over and over at the same point, always in the same place, for hundreds of millions of years. All that heat, all that volcanic energy that on Earth is distributed along a chain of islands or mountains, on Mars is concentrated in a single point. Over billions of years of geological activity, all this material has accumulated in the same place. Mons Olympus is not the result of an exceptional volcanic episode. It's the result of a hotspot that stayed in the same place for an almost incomprehensible time, piling lava upon lava, layer upon layer, without ever moving, without ever distributing its energy elsewhere. Billions of years of continuous accumulation, coupled with insufficient gravity to stop growth, have produced the largest known volcanic structure on any planet in the solar system, and possibly, according to what current science knows, the largest volcanic structure in the observable universe. This statement needs an honest qualifier. There are huge volcanoes in other parts of the solar system. Jupiter's moon, Io, has the highest level of active volcanic activity of any body we know of, with constant and violent eruptions caused by Jupiter's own tidal forces. But the volcanoes of Io, while extremely active, do not build structures as monumental as Olympus Mons. Venus has massive volcanic structures, such as the Mons volcano, which is about 8 kilometers high, impressive for Venus, but still less than 40% of the height of Olympus Mons. In other planetary systems outside of our own, it is mathematically possible that there are even larger volcanoes on exoplanets with the right conditions. But we don't have data to confirm this. What we can safely say, based on the available scientific knowledge, is that Olympus Mons is the largest confirmed volcano on any planet that humanity has ever studied. And it's just 78 million kilometers away from us, waiting, huge and silent, on the surface of the red planet. But there is a detail about Olympus Mons that numbers alone cannot capture, something that only becomes evident when you try to imagine what it would be like to be on its surface. If you landed on the summit of Olympus Mons, you wouldn't know that you're on top of a gigantic volcano. The structure is so wide, and the angle of inclination of its slopes is so smooth, about 5 degrees on average, that the Martian horizon would disappear before you could see any of the edges of the volcano. In all directions, you would see only a slightly sloping surface, extending as far as the eye can reach. There would be no visual sign that you are standing on a mountain, let alone on the largest mountain of any planet that humans have ever studied. The scale is too large to be perceived locally. Olympus Mons can only be truly appreciated from space. From there, it appears as an immense circular structure, often with its summit above Mars haze and atmospheric clouds, a dark, silent disk that rises above the planet as if to leave Mars behind. At the top of Olympus Mons is a structure called a caldera. A caldera is a depression that forms at the summit of volcanoes when the magma chamber below partially empties after an eruption and the ceiling of the chamber collapses inward. The Olympus Mons caldera is approximately 80 kilometers in diameter and 3 kilometers deep. It is not a single caldera, but a complex of overlapping calderas, each representing a different collapse at different times in the volcano's geological history. Each of these overlapping cauldrons tells a chapter in a story that has spanned billions of years, a geological archive written in Martian rock and vacuum. The last time Olympus Mons had significant volcanic activity, according to estimates based on the density of impact craters on its slopes, may have been only 25 million years ago. On a planetary geological scale, this is practically yesterday. When the last volcanoes on Olympus Mons erupted, the first hominids had not yet appeared in Africa. The large mammals grazed on terrestrial prairies that were barely beginning to take shape. And at that moment, on Mars, a colossal amount of lava probably flowed silently down the flank of a mountain that no sentient being existed to observe. Some researchers believe that it may not yet be completely extinct, not active in the sense that it is erupting now, but potentially in a dormant state, a sleeping giant, with heat still trapped in its depths, awaiting conditions that may never be repeated. What this means for the future of Mars is a question that science is still trying to answer. And to answer this and other questions, we need to understand the planet that hosts this colossus. because Mons Olympus does not exist in a vacuum. It is a product of Mars. And Mars is a world that, the more you study, the more it seems to have been built to confuse and fascinate in equal measure. Mars is the fourth planet in the solar system in order of increasing distance from the Sun, with a diameter of approximately 6,779 kilometers. It is just over half the Earth's diameter. In terms of mass, Mars is only 10.7% of the mass of Earth. He is small, cold, and thin, very thin. Its atmosphere is composed of approximately 95% carbon dioxide and has a surface pressure equivalent to less than 1% of the atmospheric pressure on Earth at sea level. If you were standing on the Martian surface without a spacesuit, your death would not be from lack of oxygen first. It would be by decompression. The bodily fluids would begin to vaporize. The absence of sufficient atmospheric pressure to keep them in a liquid state would be fatal in a matter of seconds. The temperature on Mars varies dramatically and viciously. At the equator, during the Martian summer, the temperature at the surface can reach 20 degrees Celsius at noon. It looks almost inviting, but at night, in this same place, the temperature drops to -73 degrees Celsius. The daily thermal variation is almost 100 degrees. At the poles, during the winter, the temperature can reach -125 degrees Celsius. Carbon dioxide from the atmosphere freezes and forms layers of dry ice at the poles. When the Martian spring arrives, this ice sublimates directly from the solid to the gaseous, without passing through the liquid state, and feeds massive wind systems that have swept the planet's surface for billions of years. Mars has a day that is surprisingly similar to our own. A Martian day, called the Sun, has 24 hours, 39 minutes, and 35 seconds. For those who are thinking about future human colonies on Mars, this is a fact that provokes an eerie sense of familiarity. The human biological clock would have relatively little adaptation to make on Mars from the point of view of the length of the day. The Martian year, however, is almost twice as long as Earth's, with 687 Earth days. Stations on Mars exist, just as they do on Earth, because the planet's axis is tilted relative to the plane of its orbit. But the Martian orbit is significantly more elliptical than Earth's, which means that the distance from Mars to the Sun varies considerably throughout the year, making Martian seasons more asymmetric and more extreme than Earth's. But if you really want to understand Mars, don't start with the numbers. Start with the story. 4.5 billion years ago, when the solar system was forming from a collapsing cloud of gas and dust, Mars emerged relatively quickly. It is believed to have reached its current size in just a few million years, much faster than Earth. This is important because it means that Mars preserves evidence of a phase of the solar system that Earth, with its intense tectonic and geological activity, obliterated long ago. Mars is, in a sense, a window into the solar system's primordial past, a planetary time capsule that no force has been able to completely erase. And this capsule holds a secret that, for decades, seemed impossible. Mars had liquid water on the surface, lots of it. For a long time, this is not romantic speculation. This is what the evidence points to with impressive scientific consistency. The orbiters photographed extensive networks of valleys that can only have been sculpted by flows of liquid water. We find minerals that only form in the presence of liquid water for long periods, such as clay minerals and hydrated sulfates. We saw fossilized river deltas, fan-shaped structures where river channels flowed into larger bodies of water, immortalized in Martian rock as the trail of something that once existed and then disappeared forever. The Mars Reconnaissance Orbiter has identified stratified sediments that behave exactly like sediments deposited by water in ancient lakes or seas. The Curiosity rover has spent years exploring the bed of an ancient lake inside Gale Crater and found the unambiguous chemical signatures of an environment that was once hospitable to the chemistry of life. Perhaps the most striking data comes from measurements of hydrogen isotopes in the Martian atmosphere. By comparing the ratio of deuterium, a heavier isotope of hydrogen, to ordinary hydrogen, the scientists calculated that Mars must have lost a tremendous amount of water over the course of its history. Estimates indicate that Mars may have had a layer of water equivalent to a global ocean with an average depth of up to 137 meters, and possibly much more in the northern plateau regions. An ocean that would have covered the northern hemisphere of the red planet billions of years ago. This ocean has a name in the scientific literature. It is called Oceano Borealis, the sea north of Mars, and he disappeared. To understand why he disappeared is to understand what Mars is today. And this understanding begins at the core of the planet. The Earth has an outer core of liquid iron that, combined with the planet's rotation, generates a powerful global magnetic field called the magnetosphere. This magnetosphere acts as an invisible shield around the planet, deflecting the charged particles that the solar wind constantly brings from the sun. Without this protection, the solar wind would progressively tear away the outer layers of the Earth's atmosphere. With it, our atmosphere remains thick enough to maintain pressure and temperature compatible with life. Mars has had a global magnetic field in the past. We know this because there are regions of the Martian crust, mainly in the southern hemisphere, that have remnant magnetization, traces of the ancient magnetic field etched into the rock during its solidification. They are like a fossilized photograph of a shield that no longer exists. Estimates indicate that the Martian magnetic field disappeared approximately 4.1 billion years ago, probably because the planet's core cooled enough for the convection that generated the magnetic field to cease. The planet is small. It lost heat faster than Earth, and when the magnetic field went out, Mars' atmosphere was exposed to the solar wind without any protection. The result was catastrophic and slow atmospheric erosion. For billions of years, the solar wind has been systematically stripping molecules from the Martian atmosphere, sending them into space. The atmosphere was getting thinner and thinner. The pressure was dropping, and as the pressure dropped below a critical threshold, the liquid water on the surface began to become unstable. At very low pressures, water cannot exist in a liquid state at moderate temperatures. It sublimates directly from ice to steam without going through the liquid state, or if the temperature is high enough, it boils instantly. The Martian ocean evaporated and its vapors were progressively lost to space. What was left froze at the poles and underground. Mars was, in a very real sense, desiccated alive by the sun itself. NASA's MAVEN mission, which orbits Mars specifically to study the atmosphere and its interaction with the solar wind, measured the current rate of Martian atmospheric loss. Today, Mars still loses about 100 grams of its atmosphere per second to space. 100 grams per second may seem little, but in billions of years, with variations in the most active phases of the Sun, the accumulated amount represents the destruction of a dense atmosphere and a global ocean. It's a slow-motion planetary extinction, a geological tragedy that is still happening now. As you read these words, as particles of the solar wind silently rip more molecules from a planet that was once wet and can no longer be. But Mars does not hold only tragedies. It also holds the largest topographic extremes in the solar system, and Olympus Mons is only the most famous of them. VallesMarineris, for example, is a system of canyons that stretches nearly 4,000 kilometers along the Martian surface, up to 7 kilometers deep and 200 kilometers wide at some points. If VallesMarineris existed on Earth, it would cross the United States from coast to coast with still space left. The North American Grand Canyon, which we consider one of the greatest geological wonders on Earth, is 446 kilometers long and less than 2 kilometers deep. VallesMarineris is approximately 10 times longer and 4 times deeper. The mechanism of its formation is different from the Grand Canyon, which was carved by the erosion of a river. VallesMarineris appears to have formed primarily through tectonic stresses, crustal fracturing, and collapse, possibly related to the uplift of the Tharsis region, the immense volcanic plateau where Olympus Mons is located. And this is where it all connects in a way that reveals the magnitude of what Mars represents as a planetary geological laboratory. The Tharsis region is itself an anomaly of almost incomprehensible scale. It is a volcanic plateau that rises approximately 10 kilometers above the average level of the Martian surface and is about 5,000 kilometers long. Olympus Mons lies on the northwestern edge of this plateau. In the central region of the Tharsis Plateau, there are 3 other giant volcanoes aligned diagonally, collectively called the Tharsis Mountains. They are Ascraeus Mons, Pavonis Mons, and Archaea Mons, each with heights between 14 and 18 kilometers, which would make them the largest volcanoes on Earth by a huge margin if they were here. On Mars, they are the smaller brothers of Olympus Mons, gigantic structures living in the shadow of the greatest of all. The total mass of volcanic material deposited in the Tharsis region over the course of Mars' geological history is so extraordinary that scientists have calculated that it has literally warped the planet's axis of rotation. The Martian crust became so overloaded into a single hemisphere that the planet over billions of years reoriented itself around its inner axis to rebalance the distribution of mass. This phenomenon is called true pole drift, and estimates suggest that Tharsis may have shifted the Martian axis of rotation by as much as 20 degrees over the course of its growth history. This means that regions that are now in the tropics of Mars may have been close to the poles before, and vice versa. The geology of Mars didn't just build the largest volcano in the solar system, she moved the entire planet to accommodate her. This is what happens when a geological force has no brakes. The Earth has brakes. Our tectonic plates distribute the stress. Our magnetic field protects the atmosphere. Our greater gravity limits the growth of mountains. Mars had none of these brakes operating in the same way, and the result is a world of absolute extremes, of geological records that no other planet we know of has been able to match. Now return to Olympus Mons with this context in mind. It's not just a big volcano. It is the end product of an unbridled planet, of a crust that never moved, of a gravity that could not resist, of a hotspot that never moved. Olympus Mons is Mars taken to its absolute extreme. This is what happens when all conditions point in the same direction long enough. It is inevitable and impossible at the same time. The slopes of Olympus Mons are covered in fossilized lava flows that extend hundreds of kilometers from the center. Some of these flows are so well preserved that scientists are able to analyze their mineralogical composition with orbital instruments and infer the temperature and viscosity of the original lava. The basaltic rocks that make up Olympus Mons are very similar to the basalt that comes out of Hawaiian volcanoes on Earth, confirming the hotspot nature of the volcano's origin and revealing that, for all the difference in scale, the fundamental geological processes that built Olympus Mons are the same ones that build volcanoes here on Earth. The difference is not in the chemistry. It is in the planetary conditions that have allowed this process to continue without interruption for a much longer time. The escarpment zone at the edges of Olympus Mons has also been studied extensively. There is evidence that parts of this escarpment were formed by landslides of epic proportions, in which immense volumes of rock slid into the plain around the volcano. Some of these ancient landslides may have been larger than any similar geological event recorded on Earth. The debris from these avalanches is still scattered across the plains around Olympus Mons, a silent testimony to catastrophes that happened with no one to be affected by them, with no living being that could watch the Martian sky shroud in dust, kicked up by billions of tons of moving rock. There is also a fascinating region called the Olympus Mons Aureole, a set of jagged hills and plateaus that surrounds the volcano for hundreds of kilometers beyond its main escarpment. The precise nature of the aureole is still debated by scientists, but the most widely accepted hypothesis is that it was formed by large lava slides over layers of ice or easily eroded material, creating chaotic structures around the base of the volcano during its ancient history. The aureole covers an even larger area than Olympus Mons itself. The volcano, in a broad geological sense, is larger than any single number can capture. There is also something deeply disturbing about the timescale involved in the formation of this entire region. Planetary geologists estimate that the Tharsis region as a whole may have taken more than 2 billion years to reach its current form. 2 billion years of concentrated volcanic activity, of magma rising and cooling and accumulating and repeating the cycle. To have a reference, 2 billion years ago, life on Earth was There were no animals, there were no plants, there was nothing with eyes or nervous system. And as Earth took its first faltering steps toward biological complexity, Mars was quietly building the largest volcano in the solar system, layer by layer, lava flow by lava flow, in a geological patience that the human mind has no adequate instruments to feel. But let's go back to the moment when humanity discovered this colossus up close. The first time Olympus Mons was clearly observed was by NASA's Mariner 9 spacecraft, which entered Mars orbit in November 1971. When Mariner 9 arrived, Mars was in the midst of one of the largest global dust storms ever recorded. The dust covered the entire surface of the planet, making the mission initially frustrating for scientists who were anxiously awaiting the first detailed images of Mars. Scientists waited. The weeks passed. The storm was slowly dissipating, and when the atmosphere finally cleared enough to reveal the Martian surface, Mariner 9's camera recorded for dark spots jutting out above the dust mantle. They were the 4 highest peaks on Mars, emerging from a planetary storm as islands above the clouds. The largest of them was Olympus Mons. Imagine being the scientist who saw that image for the first time, to look at a dark spot above a global storm and realize that you are looking at the summit of a mountain that surpasses the scale of anything you knew to be possible. Realize that the reason that point is above the clouds is not because the clouds are low, but because the mountain is too high for the storm to reach. Since then, numerous missions have sent cameras and instruments toward Mars and Olympus Mons, the Viking probes in the 1970s, which landed on Mars and sent back the first images of the Martian surface directly from the ground, the Mars Global Surveyor in the 1990s, which mapped the topography of Mars with a previously impossible precision, confirming the exact dimensions of Olympus Mons with laser instruments, the European Space Agency's Mars Express, which photographed Olympus Mons with stereoscopic cameras that allow it to create realistic three-dimensional models of the structure, the Mars Reconnaissance Orbiter, whose cameras have enough resolution to photograph objects the size of a dining table on the Martian surface, revealing details of lava flows and escarpment structures that were previously invisible to us. Each mission added more data, more detail, more layers of understanding, and each new layer of understanding makes Olympus Mons seem even more extraordinary than it seemed before. What these missions revealed about the origin of Olympus Mons confirms and deepens what geological theory predicted. Lava flows on the slopes of the volcano showed different generations of activity separated by long periods of stillness, followed by new bursts of activity that have deposited fresh layers on top of the old ones. The caldera at the summit shows at least 6 overlapping major collapses, each representing a period when an underlying magma chamber partially emptied and the ceiling caved in. Analyzing these collapses helps scientists reconstruct the history of Mons Olympus magmatic activity over time, almost like reading the pages of a diary written in geological language. Mars global dust storms also have a curious relationship with Olympus Mons. When these storms happen, the entire surface of Mars is shrouded in a haze of reddish dust, suspended in the atmosphere, sometimes for months. During these events, Olympus Mons emerges from the dust as an archipelago above a sea of mist. The summit and upper slopes of the volcano are exposed to the almost pure vacuum of Martian space, while the rest of the planet disappears below a continuous blanket of suspended particles. It's a spectacle that can only be enjoyed from orbit, but one that satellite cameras have captured on several occasions, 4 volcanic islands emerging from a planetary storm, with Olympus Mons being the largest and most prominent of all. The rovers that explore the surface of Mars to date have not yet come close to Olympus Mons. The Tharsis region is relatively far from the landing sites used so far, which were selected based on different scientific and landing safety criteria. But when human missions reach Mars, Olympus Mons will be at the top of the list of exploration destinations. The scientific questions it can answer are numerous. When exactly was its last eruption? Is there still active magma at some point in your feeding system? What are the exact properties of the rocks in their oldest layers, and what do they reveal about the composition of the early Martian mantle? Are there any signs of ancient hydrothermal activity in the rocks around your caldera? There is also the issue of water inside Olympus Mons. There is evidence that glaciers formed around the edges of the volcano in past periods of Martian history, when climatic conditions were different from today. These ancient glaciers left marks on the slopes of the volcano that satellites can detect in the morphology of the terrain. If there was ice in significant quantities on the edges of Olympus Mons in the past, it raises questions about possible habitable environments that could have existed at the interfaces between the volcanoes, geothermal, heat, and the surrounding glaciers. On Earth, similar environments such as those under glaciers in active volcanic regions are habitats for extremophile organisms, microorganisms capable of surviving in extreme conditions. If there was ever microbial life on Mars, the interfaces between volcanic activity and ice may have been one of the most promising places for such life. This makes Olympus Mons not only the largest volcano in the solar system, but potentially one of the most relevant sites for the search for evidence of past life on Mars. Not present life. Almost certainly not that, but past life, microbes that may have flourished billions of years ago when conditions were different, and that may have left chemical traces or microscopic fossils preserved in volcanic rocks and sediments. Martian astrobiology and the geology of Olympus Mons are, in this sense, deeply intertwined. There is also a question that fascinates many scientists who study Olympus Mons, and that points to the future. If Olympus Mons is not yet completely dead, what would it take for it to erupt again? The honest answer is that we don't know for sure. What we do know is that the hotspot that fed Olympus Mons for billions of years may still exist in the Martian mantle, simply with less vigor than before. If there was a sufficient influx of heat, if conditions in the Martian mantle changed in a way that would restore the necessary magmatic pressure, the giant could wake up. Not on our timescale, not in any horizon relevant to human civilization, but on a geological scale, the possibility is not discarded. And when humanity finally arrives on Mars and establishes a permanent presence, Olympus Mons will inevitably be a destination for priority scientific exploration. Its slopes preserve a stratigraphic record that can tell the geologic history of Mars more clearly than anywhere else. The different layers of lava, with different ages, are like pages from a book that recorded billions of years of planetary history. Reading this book will reveal not only the past of Olympus Mons and Mars, but potentially details about the formation and evolution of rocky planets in general. Details that apply to exoplanets in other solar systems that we may never be able to visit, but that we can try to understand from the principles learned here, in our cosmic backyard. There is also a proposal circulating among astronomers and engineers, still in the realm of serious scientific speculation, that the summit of Olympus Mons could be a privileged place for the installation of telescopes or astronomical observatories on a future inhabited Mars at altitudes of nearly 22 kilometers. The observatory would be above almost the entire Martian atmosphere, thin as it already is. The absence of light pollution anywhere on Mars for now, combined with the extreme altitude and atmospheric clarity, would make the summit of Olympus Mons one of the best places in the solar system to observe the universe with optical telescopes and other bands of the electromagnetic spectrum. The largest volcano in the solar system could become the platform for the largest observatory in the solar system. But there is something that needs to be said about Mars that goes beyond science. Something that doesn't appear in peer-reviewed papers, but that anyone who has ever spent hours looking at images of the red planet feels viscerally. Mars is eerily familiar. Not familiar as a living room, familiar as a dream you know you've had, but can't completely remember. The landscapes of Mars, with their stony plains, their dunes of fine sand, their skies dawning in a pinkish hue that does not exist in any sky on Earth, have a quality that the human mind interprets as almost recognizable. The valleys that rivers carved billions of years ago have shapes that the eye follows in the same way they would follow the course of a terrestrial river. The craters, with their circular rims and flat bottoms, have a symmetry that the mind processes as familiar, even though no human has ever seen one up close in person. The red dust that covers almost the entire surface has a color that, curiously, the human brain processes as hot, even though it intellectually knows that that surface is tens of degrees below zero. The color of Mars, by the way, deserves its own explanation, because it says something about the history of the planet. The red planet has this color because its surface is literally rusty. Martian rocks contain iron oxide in large quantities, the same chemical process that produces rust on Earth. The surface of Mars oxidized over billions of years, probably during a period when there was more oxygen available in the atmosphere or surface waters. The planet we see today is red because it was once, to some extent, more like Earth than the icy desert we find now. Rust is the chemical scar of a transformation that lasted for eons. And when you imagine Olympus Mons in this reddish context, when you try to visualize that 10-kilometer high wall emerging from a plain of rust and silence toward a salmon-colored sky, with a caldera 80 kilometers in diameter at the summit that the instruments tell us exists, but that no human eye has ever seen directly, something happens that goes beyond the intellectual. Some part of the brain that is not completely rational tries to calculate the distance, tries to estimate the volume, tries to fit that structure into some drawer of known references, and he can't. There is no drawer for Olympus Mons. It does not fit into any category of direct human experience. We live in a universe that, for the most part, is not meant to be like us. But every once in a while, nature produces something that is both too great to understand and close enough to study. Olympus Mons is one of those things. It's less than a fraction of a light second away. Cosmically speaking, it's still in our backyard. And at the same time, It represents something that the Earth has never produced and could never produce under the conditions that exist here. Olympus Mons has existed in absolute silence for billions of years. He grew up without witnesses. It erupted without anyone to see the ash clouds and the lava rivers. It formed its colossal caldera without any conscious being existing on Mars to look at it and feel anything. All the grandeur of that structure was consumed by emptiness, by the total absence of perception. Olympus Mons does not know that it is great. He doesn't know that he is the greatest. He doesn't know it exists. He simply is, and he was, and perhaps it will be for billions of years more after humanity has ceased to exist. This cosmic indifference is disturbing in a way that science is under no obligation to acknowledge, but that the human mind cannot ignore. When you look at Mars in the night sky, that constant reddish dot that the ancients called the planet of war because of its blood color, you're not looking at an icy, unimportant wasteland. You are looking at the planet that has the highest mountain in the solar system, the most extensive canyon system in the solar system, the remnants of ancient oceans that covered its northern hemisphere, dust storms that sometimes enveloped the entire planet for months at a time, obscuring the entire surface in a red haze visible even from ground-based telescopes. Auroras caused not by a global magnetic field, but by local magnetic fields preserved in the crust, fossilized fragments of the shield that the planet lost billions of years ago, turning on ghostly lights in a Martian sky that never had anyone underneath to admire them. Two irregular moons, Phobos and Deimos, so small and so different from any moon we know of that they are likely asteroids captured by Martian gravity at some distant time in their history. Phobos, the larger of the two Martian moons, is in such a low orbit and so close to Mars that the planet's gravity is progressively destroying it. With each passing century, Phobos gets a little closer to Mars. Approximately 50 million years from now, Phobos will have come too close, and tidal forces from Mars will completely tear it apart, turning it into a ring of debris around the planet. Mars will have rings in the future, and on the surface of this ringed Mars, Olympus Mons will still be there, silent and huge, indifferent to the spectacle above its head. You're looking at a world that was once wet and warm, and possibly hospitable to some form of life. A world that lost its magnetic protection and saw its atmosphere stripped away by the solar wind over billions of years in a process that has not yet ended. A world that today is cold, arid, and hostile, but that preserves in its rocks, and in its volcanoes, and in its canyons, and in its icy subsoil all the history of its transformation. A world that science has not yet been able to fully read. A geological archive that humanity has barely begun to decipher. And in the midst of all this, silent and immense and absolutely indifferent, is Olympus Mons, 2 Everests in height, snow polo half in width, a craggy wall that would make any wall built by human beings look like an erasable trace, a caldera that could swallow an entire city, a geological record that is more than 1 billion years deep, the end product of billions of years of magma rising always by the same point, because Mars never moved and never let energy disperse, and never stopped growth until the structure reached proportions that no other planet in the solar system came close to matching. Olympus Mons is not only the largest volcano in the solar system, it is a reminder that nature, when freed from the brakes that the Earth imposes, produces things that the human mind has not been equipped to climb emotionally. It is a reminder that planetary geology is a force that operates on timescales and space that make any human work absolutely invisible by comparison. It's a reminder that the universe wasn't designed with humans in mind, but that every once in a while, it produces something so extraordinary that humans can't stop looking at it. The red planet is out there now. It will be there tonight when the sky darkens, in its constant reddish spot, exactly where it has always been, and over its surface, above the dust storms, and above the thin atmosphere, and above anything the Earth has ever produced in its entire geological history, Olympus Mons continues to wait. Huge, silent, the greatest of all, waiting for the day when living things will finally step on its slopes and look up toward a summit so high that the curvature of Mars itself puts it beyond the horizon, waiting for the moment when one will finally reach the top. One will look in all directions and see only a slightly sloping surface extending as far as the eye can see, unable to see the edges of the mountain on which one will be standing. And even then, even with all the technology that humanity will have developed to get there, this explorer probably won't be able to feel the scale of what's under his feet. Olympus Mons is too big even to be felt from the inside. This, perhaps, is the most disturbing thing of all about the largest volcano in the universe. Not that it is huge, it's just that it's too immense to be perceived even by those inside it. But the history of Olympus Mons and Mars inevitably leads us to an even bigger question, one that scientists rarely manage to avoid when they study this planet long enough. Where was humanity when Olympus Mons grew? The answer, of course, is that humanity did not exist. The earliest recognizable ancestors of humans appeared no more than 6 or 7 million years ago. The last major confirmed eruption of Olympus Mons happened even before that. But the question goes deeper than the chronology. It touches on something about our relationship to time and to the cosmic scale that is genuinely difficult to process without some existential discomfort. Olympus Mons has been around for so long that complex life on Earth has undergone multiple mass extinctions as it has continued to grow. The Great Permian-Triassic extinction 252 million years ago, which wiped out about 96% of all marine species and 70% of terrestrial species, happened after Olympus Mons had already begun forming. The Cretaceous extinction 66 million years ago, which wiped out the non-avian dinosaurs, happened while Olympus Mons may still be having its last significant eruptions. Life on Earth has survived repeated catastrophes, been reborn, diversified, and eventually produced a species capable of pointing telescopes into space. And throughout it all, Olympus Mons stayed exactly where it was, accumulating silence and Martian dust on its basaltic slopes. There's also something worth paying attention to when we think of Olympus Mons in the context of the search for habitable planets outside the solar system. Astronomers searching for exoplanets capable of sustaining life often look for planets in the so-called habitable zone of stars, the range of distances where temperature allows water to exist in a liquid state. But the case of Mars shows that the habitable zone is not enough. Mars is within the habitable zone of the Sun, or near its inner edge depending on the definition used. And Mars didn't sustain complex life, at least not that we've found evidence. What Mars shows is that the size of the planet matters as much as its distance from the star. A planet that is too small cools too quickly, loses its magnetic field, loses its atmosphere, loses its water. Olympus Mons is the geological monument to this process. A structure built while the planet still had enough heat to produce it, preserved now in a world that no longer has enough heat to repeat it. When astronomers search for habitable exoplanets, the case of Mars suggests that planets significantly smaller than Earth are weaker candidates than they appear to be just because of their orbital location. Size matters. The ability to retain internal heat matters. The possibility of maintaining tectonic activity and the magnetic field matters. Mars failed all of these criteria, not because it was in the wrong position, but because it was born too small. And Olympus Mons, paradoxically, is both the symbol of Mars' geological power and proof of its limitation. He grew so big because nothing stopped him, but nothing stopped it because the planet that hosts it is too small and geologically simple to have the structures that would distribute and generate heat in a more sustained way. The magnitude of Olympus Mons and the fragility of Mars are the same story told from two different perspectives. There is a concept that planetary geologists use called planetary cooling time, which describes the speed at which a planet loses the heat accumulated during its formation and during the radioactive processes in its interior. Larger planets have more mass to retain heat for longer. The Earth, with its interior still active, its volcanoes in full activity, its liquid core spinning and generating a magnetic field, still has enough heat to sustain all of this for billions of years more. Mars, with only a tenth of the Earth's mass, cooled much faster. The core solidified, convection ceased, the magnetic field disappeared. Volcanic activity gradually reduced over billions of years until it reached a state of almost total quiescence. What's extraordinary is that even as it cooled, Mars still managed to build Olympus Mons. The energy that remained in the Martian mantle, even if decreasing, was enough to power that single hotspot for time, far beyond what would be needed to build any known volcanic structure on Earth. It was the last major work of a planet in geological decline. Olympus Mons can be seen as the swan song of a world that was once more active, warmer, more geologically alive. NASA's Mars InSight mission, which landed on Mars in 2018 and was operational until 2022, brought back completely new data about the planet's interior. InSight was equipped with an extremely sensitive seismometer, capable of detecting Martian tremors, the equivalent of earthquakes on the Red Planet. During its operation, InSight has recorded hundreds of seismic events on Mars. Most were small and probably generated by cooling and contraction of the crust, but some were more significant and provided data about the planet's internal structure that we had never obtained before. InSight revealed that Mars' core is larger than expected, with a radius of approximately 1,830 kilometers, and that it is liquid, at least in part. That was a surprise. It was widely believed that the core of Mars was fully solidified. The discovery that there is still liquid material in the Martian core has reopened questions about the planet's residual geological activity and what may still be happening deep within the world. Hosting Olympus Mons, a partially liquid core, does not necessarily generate a global magnetic field. This would require vigorous convection within the liquid core, which appears to no longer be occurring on Mars on a sufficient scale. But the existence of liquid material means that Mars is not yet completely geologically dead. Something is still going on inside. Something that perhaps still feeds, in a very small way, the hotspot systems that built Olympus Mons. It's hard not to see Olympus Mons as a symbol of something broader than Martian geology. It is the physical record of what planets do when they have enough energy and time and the absence of enough constraints. Here is the question and the answer at the same time. The question is, how big can a volcano grow? The answer is there. On Mars, 21.9 kilometers high and 600 kilometers wide. And this answer is neither reassuring nor reassuring. It is just what it is. A geological fact that defies the human scale in all dimensions, temporal and spatial. A structure that began to grow when life on Earth was still exclusively single-celled, and that was still growing when the first mammals diversified over the corpses of dinosaurs. An object that no human being has ever seen up close, that no human instrument has ever touched, that exists at a distance that no human being has ever walked on his own 2 feet. And that, despite all this, we know, we measure, we mapped, we date your layers, we analyzed its composition. We calculated the pressure of the magma that fed it. We estimate the time of their formation. We have proposed theories about its possible future. That's what science does. She achieves what her feet cannot achieve. It measures what the eye cannot see. It transforms the incomprehensible into data, and the data into comprehension, even if that understanding is never complete and never fails to generate new questions. Olympus Mons raised more questions than it answered. When was its last eruption? Will it erupt again? Is there any form of fossilized microbial life in your rocks? Does the hotspot that fueled it still exist? What do the strata of your caldera reveal about Mars' climate history? What exactly was the role of ancient glaciers in shaping their craggy edge? These questions are waiting for answers, and the answers are waiting for missions. Robotic missions first, human later. Instruments that land on the slopes of Olympus Mons and drill into its rocks. Geologists who walk along the edge of their caldera and take samples of the different layers of solidified lava. Seismometers installed inside that detect any residual tremor of deep heat. This will all happen, not in decades, perhaps, but at some point that can still be called the human future. Someone will be there, and when you are, you will realize that the largest monument in the solar system was not built by anyone. It was not planned, it was not designed. It was the blind and relentless result of physics and time and gravity and absence of brakes. The largest volcano in the known universe is the work of geological chance, and it is greater than anything that human intelligence has ever built or will ever be able to build. The universe does not need intention to produce grandeur. Olympus Mons is the proof. And when you look up at the sky tonight and you find that reddish dot between the stars, remember that on the surface of that dot is a mountain as tall as 2 Everests. It exists in silence. It exists in solitude. It exists without knowing that it exists. And you, looking at it from a planet tens of millions of miles away, are the only being in the universe who is aware of it. What a disturbing privilege this is.